Hello, everybody. Dr. White here with just a quick little exploration uh, to give you a little bit more convincing about why the success failure criterion for a binomial random variable to be normal really is working like the textbook says that it does. So you can explore this with an app that's similar to Binom Norm that you've worked with before. This one is called BinomSkew. In our studio over in your console, just type in BinomSkew. You can get that with the code completion. Let me make this just a little bit bigger so you can see more easily on the screencast. All right, I'll smallify it now. And let's run it. So it works real similar to Binom Norm. It starts you off with the distribution of a binomial random variable. This one has 50 trials, and the chance P for success is something that you can set, okay? You can set it by pushing the cog and you get a little manipulator. Right now, it's set at 0.01. 1% chance of success. So if you got 50 times you're trying and only a 1% chance of succeeding each time, you're most likely to get, no successes or maybe one, but not much more. And sure enough, the probability of no successes is like really big, about over 0.6. Chance of one success is over 0.3, and the chance of more than that is like really, really small. In addition, the app is computing the expected number of successes, N times P. 50 times 0.01 makes a 0.5. So you expect half a success in your 50 trials. The expected number of failures is N times 1 minus P. That would be the 50 times 0.99. And that turns out to be 49.5. So you expect a lot of failures, but you expect very few successes. When that happens, you'll find that the distribution for your binomial random variable is skewed off to the right by a good amount. You can see that big, long tail of very low probability outcomes here. If you compare this to a normal curve that has the same expected value and standard deviation as this binomial random variable, you see there's quite a big difference. Okay. Now let's just raise the chance of success up a bit. So I could click here and then use my right arrow to move it up to 0.02, 0.03, 0.04, 0.05. You can see the chances change right here. You're up to 0.05 chance of success on your 50 trials. And what's happening is the distribution, it's still right skewed, but not by as much. The expected number of successes is now up to 2.5. The expected number of failures is decreasing. Let's keep on increasing the expected number of successes. I'm now up to a binomial random variable where the expected number of successes is 10. The P here was 0.2, 20% chance of success on each of my 50 trials. 50 times 0.2 is the 10. By the time you got up to 10, look at the shape of the distribution of the binomial random variable. It's pretty bell-shaped. You can still see some right skewness, but it's not much. So once both these numbers got above 10, people are feeling, this is approximately normal. I'm satisfied with the normal approximation. If I compare it to a normal curve that has the same expected value and the same standard deviation, there's not much difference. Let's try it the other way around. Let's move the chance of success to 99% on each trial. You get a mirror image of what happened before. Now you're overwhelmingly likely to have all 50 of your trials be successes. Not very likely at all to get much less than 50 successes. Expected successes, 49.5. Expected failures, really small. But now, take your chance of success down by using the left arrow key, and you'll see that the expected number of successes goes down and the expected number of failures goes up. I'm at 0.88 for my probability of success on each trial, and the left skewness is beginning to go away. We keep going. Now I'm at 0.8 for my chance of success on each trial. I'm now expecting 50 times 0.8 is 40 successes. 50 times 1 minus 0.8, 50 times 0.2 is 10 failures. My expected failures have gotten up enough now. They're at 10, and look at that. When I compare the distribution to the normal curve, again, it looks pretty similar. Of course, the higher the expected successes and failures both are, the more normal this is going to look. Let me move this to maybe a 0.5 chance of success on each of my 50 trials. Now there's almost a perfect match. So now I hope this demonstrates to you why the success-failure criterion is like it is. When the expected number of successes and failures is at least 10, people think that the distribution of a binomial random variable is reasonably close to a normal distribution. But also, the higher both of those numbers are going, the closer to normal the binomial distribution will be. This has huge implications because sample proportions are almost like binomial random variables. They're a binomial count of the number of people who said yes in your sample divided by the sample size. Okay, that's all for now.